We're going to be talking about how to prove statements that have quantifiers in them. But before we did that, I wanted to show you how we can use those theorems that have quantifiers. So here's the setup. I've written down the three theorems that I think you'll all believe. The first one is that for all x squared is greater than or equal to 0. Okay? The domain of discourse here is the real numbers. So yeah, that seems true. Now here's another one. If I have three real numbers, x, y, and z, for all x, for all y, for all z, if x is greater than or equal to z and y is greater than or equal to z, then their sum has to be greater than or equal to 2z. Okay? Again, I'm pretty sure you'll believe that that's a true theorem. Here's another one. For all x, if x is greater than or equal to 0, then there exists a y such that y squared is equal to x. Again, this is true for the real numbers, right? I can always find a y that has this property. We call that y the square root of x. Okay, so let's see what I can do with these three theorems. Now, I'm going to try to set up a situation here where I have a triangle. Okay, it's a right triangle. And this point here is going to have coordinates x1, y1. This point here has coordinates x2, y2. And I want to use the Pythagorean theorem. So if this is A, this is B, and this is C, then they're related by a squared plus b squared equals c squared. And in particular, c is equal to the square root of a squared plus b squared. It's a positive square root. Now, the problem is that I can't quite use square root until I know that a squared plus b squared is greater than or equal to 0. So I may have a term like this. I may have a term that is x2 minus x1 squared plus y2 minus y1 squared. I don't want to show that this is greater than or equal to 0. Okay, so that's what I would like to show. And the way that we'll do that is as follows. First of all, we know that we're actually going to use this. We're going to use the fact that if x is greater than or equal to z, and y is greater than or equal to z, then x plus y is greater than or equal to 2z, okay? And we'll set x being equal to x squared minus x1 squared. X2 minus x1 squared. Y is y2 minus y1 squared, and z is equal to 0. Okay, so because I have for all x, for all y, for all z, I can choose the x, y, and z that are most useful to me, right? So this theorem actually becomes x2 minus x1 squared is greater than or equal to 0, and y2 minus y1 squared is greater than or equal to 0. I need parentheses around this. This implies that x2 minus x1 squared plus y2 minus y1 squared is greater than or equal to 2 times 0. Okay, so that's actually the instance of the theorem, and that's the word that we use, the instance of the theorem that we want. Okay, now x squared is greater than or equal to 0 for all x, right? So what we can do now is actually replace this by true. So we can say true and this is using for all x squared is greater than or equal to 0. And we set x to be x2 minus x1. Also, y2 minus y1, so again, that's also true. So true and true implies that x2 minus x1 squared plus y2 minus y1 squared is greater than or equal to, and 2 times 0 is just 0, so we have that. Okay. Well, true and true is just true. True implies something, means that that has to be true. So this is the same as simply saying x2 minus x1 squared plus y2 minus y1 squared is greater than or equal to 0. So you see, this little, dialogue here is actually the proof of this fact. Okay, and what we have is that we used those two theorems that we started with that talked about the for alls, right? By actually choosing different instances of those. And that's the key for all. You can pick whatever you want it to be. So now, I would like to say c is equal to the square root of those terms, right? So I can now use this theorem, okay? And what I have, and I'll let x be actually equal to this expression. So x is equal to x2 minus x1 squared plus y2 minus y1 squared, okay? And so now I have the theorem that says that if x2 minus x1 squared plus y2 minus y1 squared is greater than or equal to 0, that implies that there exists a y such that y squared is equal to x2 minus x1 squared plus y2 minus y1 squared. Okay? This hypothesis we actually have right here. We already proved that. So remember that this is not hypothesis or conclusion. Hypothesis is actually true, so we'll be able to derive from that the conclusion of this. So in particular, we'll be able to derive that there exists a y such that y squared is equal to x2 minus x1 squared plus y2 minus y1 squared. Okay. So now that's going to be a theorem, right? You know, that's something that we can use because we've proved that. So now how do we take advantage of that there exists? And the answer is that we know that there's some number that has this property. We don't know what that number is. But what we can do is we can actually write it down and just simply give it a name, okay? It has to be a new name, and this is very important. So let's give it a new name. We'll call it Fred, okay? So what we have is that Fred squared is equal to x2 minus x1 plus y2 minus y1 squared, okay? And that is what we wanted to get, okay? Fred is in fact c, right? C is equal to Fred, okay? And that's how we use there exists. When we have a theorem that has a there exists an x such that we can create a new instance of it. And when we do, we simply have to replace x by some new name, okay? Now, I've emphasized the fact that it has to be a new name. And let me show you very briefly what that is. Let's say that we have proved that there exists an x such that x is odd. This is true, right? Okay. We've also proven that there exists an x such that x is even. Okay. And now what I'd like to do is to show that I'm going to prove this. Okay. And even x. Okay. So there exists an x such that, actually I'm going to prove that there exists an x such that. Okay. And the way that I'll do it is as follows. Because odd x, then I'll say, oh, odd Fred, okay? Because I can simply create a new constant, okay? There exists an x such that even x. So I'm also going to add to my list of theorems the idea that even Fred. Okay. Well, if I have those two theorems, right, from these, I can definitely get that odd Fred and even Fred. That can't possibly be true, right? Fred can't be odd and even at the same time. From this, then I could definitely conclude that there exists an x that has that property. But again, we know that that can't possibly be true. So what's gone wrong is right here. This step is incorrect. And this step, on the other hand, is just fine. Okay? And this is why. When I said odd Fred, I said Fred is a new symbol, right? Which in fact it was. You didn't see Fred anywhere else up to that point. And that means that I can say that Fred is an odd number. Okay? Whatever Fred is. Fred might be equal to 1, it might be equal to 7, it might be minus 55. Doesn't matter, right? All I know is that Fred is an odd number. I don't know which one, okay? But then when I tried to use there exists an x such that x is even, and I said, oh, even Fred, that's where I made the mistake, because I've already used the name Fred. I should have picked a different name, like Sally. If I said Sally, then I would have concluded that Fred is odd and Sally is even. Okay, right? There's no contradiction there. That's perfectly fine. Perhaps Fred, like I said, it's a number. I just don't know which one it is. Maybe it's 17. Sally is also a number. I don't know which one it is. Maybe it's 12, right? But the point is, there's nothing that says that they're the same number, right? Whereas if I give them the same name, then they have to be the same number. So that's just a caveat, all right? The way that we use theorems that say for all, you are allowed to choose anything, any constant in place of that variable, right? Whichever one is going to help your proof, right? You pick the one that's going to help you. If you're trying to use a theorem that says there exists an x, then you cannot pick arbitrarily what x you want it to be. Instead, you have to create a new name, something that doesn't appear anywhere else in your proof, and you can say, well, that new object has this property. Okay, don't mess those up. I mean, it's pretty easy to do, but it's really, really important.